let's talk about Lagrange mechanics part 6.
How dare you? I am slapping you in the face with a white glove.
We're starting the video, Tyrion. He slapped me. Anyways, we always start with the last time. So we're doing Lagrange mechanics part 6. Today we're going to talk about a little bit about the conclusion of the formalities that we've talked about, because we've laid out all of the formalism, right? The first 5 Lagrangian, or the first 5 discussion series, and then we did like some other small videos in between, like we built the brachistochrone and did all that type of stuff.
This is Jax leaving stream. Sorry, physics dad.
Oh, okay. Bye, Jax. Good to see you, of course, as always. And thank you again for helping out. Anyways, okay, so let's see here. Last time on Physics Office Hours, we had 4 examples, right? We did the Atwood's machine. We did a particle under a simple harmonic motion, confined to the surface of a cylinder. We did, what else did we do? We did 2 other examples. I should just look.
I am the only here, haha.
Oh, jeez. Oh, you. There we go. We did a block sliding down a wedge, and we did a bead on a spinning wire hoop.
Cylinder motion.
Cylinder motion. I talked about that one, man. We did a block sliding, or 2 blocks that were free to slide, and then a bead on a hoop.
Atwood machine.
You're not helpful. The big point about the idea for last week was coming up with a prescription, right? We had a prescription for solving our equations of motion with the Lagrange mechanics, right? We had to write down, and this is really important for everything we did, write down the Lagrangian with kinetic energy and potential energy, right? That was huge. We write it down, and we always stick with an inertial frame of reference. That was a big, important part of the original Lagrangian mechanics lesson, right? The second part was to choose generalized coordinates, right? And choosing the generalized coordinates was important. That way, the next step was to rewrite the Lagrangian in our generalized, rewrite the Lagrangian in generalized coordinates.
I have a fever, and the only that can heal the fever is more cowbell.
Do I have to take speech away? Swear, Tyrion. I will take speak away. All right, number 4. Write down the equations of motion. Let's say the Euler-Lagrange equations, and then subsequently the equations of motion. For each generalized coordinate. And that's our prescription, right? Like, that's what we do. We write down
Jackson
the Lagrangian.
says you can only write the L as a function of generalized coordinates.
Jackson says you can only write the L as a function of generalized coordinates? Interesting. I mean, Taylor says something very different. So maybe we should, Taylor. No, Taylor does not say that. This is literally from Taylor. You write down the Lagrangian, and you don't write it down as a function. Even this one we're going to do today, we're going to start with this, 1/2 m and then r vector. Like, that's not generalized coordinates. That's just r. And then you can rewrite r as a bunch of generalized coordinates. This is what I'm talking about. You write it as an inertial frame of reference, and then you can write it as the generalized coordinates. Because if you try to write the kinetic energy in a non-inertial frame of reference, you always end up getting some bad things. So that's what Taylor means by this. Well, Taylor must be arguing with himself then. Okay, let's see. So we're into the conclusion of our formalities, right? We did this. This is good. This is what we talked about. This is how you solve things. There's a couple of things that I'm just going to read from the notes. You can, again, go look at, just summarizing some things that Taylor talks about. Oh, by the way, we're following Taylor. John R. Taylor. This is where we're following. I'm following a textbook. It's just easier that way, and I'm not. And this is a discussion series. It's basically like a reading group. Okay. Okay. So, conservation of momentum. Let's talk about conservation laws. Yeah, you can definitely do friction stuff inside of the Lagrangian. I think last week I was a little less confident in that than I am this week, but yeah, it's definitely there. It's just a matter of changing the Lagrangian to fit it. Okay. Let's see here. So deriving the Lagrangian equations of motions from Newton laws, we kind of get the conservation laws for free, right? Like the conservation laws exist inside of the conservation laws exist inside of Newtonian mechanics. So when we derive Lagrange mechanics from Newtonian mechanics, which we did the first lesson, or maybe it was the second lesson after calculus of variations, then you can easily see that the conservation laws are going to be there as well. But we can still talk about them in Lagrange mechanics and kind of get them again. So particles are translationally invariant, meaning if we transport all of n particles of some system, so some system is comprised of n particles, and we're going to take them and transport them through a displacement of space, and we'll kind of lay it out mathematically. Nothing significant about the system changes. That's what translationally invariant means. So if we have a bunch of particles here, and this is the picture, something like this from Taylor, if you just move the particles to here, and you translate them the exact same vector, where this is all just let's do little e, epsilon vector, the same vector, then the physics of the system should remain the same, much like the physics that makes up me won't change if I'm here, right? There's nothing changing about my system. From going from here to here, from here to here, from here to here, nothing changes. I can translate through space. And my physics doesn't change. That means that I am translationally invariant. In particular, the potential energy must be unaffected by this displacement. So our potential energy, if we were to have this where we take some r displacement and then, it's plus, and displace it, r1, and we take all of the particles in the n particle system and displace all of them, n plus epsilon. Right, we expect this will, and there's some, well, he has a factor of t in here as a variable, so we'll include that. You expect this to be the same thing as the potential of just the position vectors of the particle, right? Oops, r, n. So you expect these two things to be the same. That's kind of like what translation. And then another thing we can say is that a small variation in u is not going to change, right? The velocities must remain the same under this translation as well. Y, we'll think r dot is equal to the time derivative of r with respect to time. So if that does not, this epsilon won't depend on time, right? So if you take the derivative with respect to time, that's going to be 0, so it has nothing to do. So r dot is the same in either place. So that means that there's not going to be, so then small variation in the kinetic energy is going to be 0 as well. Okay? And then subsequently, if the small variation in the potential and the small variation in kinetic energy are both 0, then if we took a small variation of the Lagrangian, then that'll be 0 as well. Okay? And this is just what it's saying, like translating particles through space is not going to change stuff. Okay? That's important. Okay, so then what can we do now? So choosing epsilon to be in the x direction, so let's just say, hey, this is now the x direction. Then we can write the equation, a small variation in the Lagrangian as just this epsilon times a small variation in each Lagrangian with respect to the generalized coordinate. Basically, we're getting the equations of motion kind of like taken care of right now, okay? Or the Euler equations is what I should say. So now, basically, if you take the derivative of the Lagrangian with respect to the generalized coordinate, doing all of this a bunch of times, the epsilon comes out front, and you set it equal to a small that is what the small variation of Lagrangian is. That's equal to 0. We know that from up there. So then, is there anything we can say about the total thing? Well, we can write it as a sum. So this implies that the sum over all of these small variations. Oh, I'm sorry. The sum of all of these derivatives of the Lagrangian with respect to the generalized coordinates of each individual particle is 0. Okay? So, where do we go now? All right, let's see. There's a zombie in my yard. Okay, now, using the Euler-Lagrange equations, if we take this derivative of the Lagrangian with respect to the any generalized coordinate, we're going to, of course, get the time derivative of the derivative of the Lagrangian with respect to the time derivative of the generalized coordinate, right? This is the Lagrange equation. Now, this, if we have our normal situation where this is the normal kinetic energy, 1/2 m r dot squared, then we're going to just get the momentum, the change in momentum with respect to time, right? This looks familiar. We've talked about this quite a bit. This itself is the momentum component of the alpha particle, that just picking one of the particles that we're moving, one of the n particles that we're moving. And this is the momentum component of that particle in the x direction because that's the direction we picked. Okay? Now what if we take the sum of all of these? So now instead of writing this one, we're just going to write the other half of the equation, except using this side of it. And if we summed over all of alpha from alpha equals 1 to n, where is it? I've lost it. There it is. Of p alpha x, we'll get some capital P of x, which is basically I forgot the time derivative. We'll get the total momenta in the x direction of all of the particles. Okay? And that's equal to 0. Now, what does this mean? What does it mean for the time derivative of the momentum to be 0? So this is just a little tidbit. Again, it's in the notes if you're new here. You're like, beta particle. That's funny. This is not an alpha particle, it's an alpha radiation or whatever.
I smell conservation.
Yeah, you should smell conservation. You should smell conservation, right? This is, if we basically say, if you translate a particle through space, I'll just read my little tidbit here. So provided that the Lagrangian is unchanged by the translation, i.e. my physics here is the same as it is here, then the total momentum of an n-particle system is conserved. So provided that you take this transformation, basically saying that as long as you move these and all of these small variations are 0, that the total change in all of the momentum of all of the particles is going to be 0. Okay, that doesn't tell you a lot about individual particles of the system, but
your volume seems to increase as you change positions.
Yeah, that's excitement, and I'm out of breath because well, never mind. So, yes. That is not to say maybe something about the individual particles, but it is to say something about a conservation of all of the particles. I love your streams, but when I recently started to learn classical mechanics, I think I'm gonna puke. Stanzel. It gets better, I promise. And then it gets fun. It gets fun. There's a point, and Tyrion can attest to this, because Tyrion's at the fun part of it, where writing down these equations seems to be very much enjoyable sometimes. Okay, let's talk about the next conservation law. So this is so that's cool. That's a very cool fact. Let's talk about the next one. How about conservation of energy? Okay? let's consider a system that now varies over time. Okay? I'm not going to go into the details of it yet, other than it's a system that varies over time. And then we're going to really talk about the details of the system, but I'm not going to talk about the details of what that means. Okay? We'll talk about that towards the end. Okay, so let's consider conservation of energy. Let's consider a system that varies over time. So if we have some derivative of a Lagrangian, and we're going to talk about all of the generalized coordinates for the Lagrangian. So some q1 to qn, we're dealing with little n particles.
Welcome to the channel.
Q dot
Things get
1
a little bit weird.
to q dot n. And this, thank you for the follow. Who is that? Oh, it's Beta Particle. Thank you for the follow, Beta Particle. It's always good to have more people here. If you have any questions, exclamation mark asking your question, and I will take a look at it when I'm done with this, or you can ask and hopefully I'll catch it. And one of my mods is there and want to throw questions in queue, you absolutely may. So now what happens if we take the derivative with respect to time of the Lagrangian? We have some chain rule stuff. I will not be talking about this particular chain rule. We did do this earlier in the series, and I hate to be that guy, but if you want to see this particular chain rule, we can talk about it after the lesson, okay? It's certainly not intuitive for me.
Slacker.
No, not slacker. Want to keep pace for people who don't need to see the chain rule again. And then we'll do the chain rule. If you want to see the chain rule, we'll do it at the end. Just throw it in the queue. So we have, if you take the chain rule of the Lagrangian, you can see that you'll get the derivative of the Lagrangian with respect to the first generalized coordinate, and then qi dot, and then epsilon, or capital sigma, and then sum over all of the change in the Lagrangian with respect to q dot times q double dot. And then lastly, oh, I lost my spot. And then lastly, the time derivative of the Lagrangian. Just straight up now, tell me. Okay? So now if we replace this first sum right here with the potential, we're just going to try to find the generalized potential, and we're going to do the same thing that we did right here, okay? So we're going to start with that. So we'll replace the first sum. We're going to take the Lagrange, or the derivative of the Lagrangian with respect to the generalized coordinate. Where is it? There it is. It's going to equal to the d dt of the change in Lagrangian with respect to the change in the generalized coordinate with respect to time. And this is going to equal d dt times the generalized momentum. So this is the change in the momentum with respect to time. Okay? Good, 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 good. So the second sum right here is the generalized momentum. This is going to have a great result. So just bear with me for a little bit longer, and we're going to see something really cool. So what do we get? So d dt is then going to be, we get this from the first sum. We get a generalized momentum right here times this from the second sum. So now we're going to see that the sum of all of the i's will get pi dot qi dot. So that comes from the first one. If this is pi dot, this is qi dot, pi dot qi dot, plus the generalized momentum that we get from here, and qi double dot. And this is the sum over all I. And then we also just get this extra term of the Lagrangian with respect to time. Okay? Thank you, Tyrion, for throwing that in the queue. Alrighty. Now, we're going to undo the product rule. So this can be a product rule. This kind of looked familiar to some of you, I'm sure, if you just have PQ dot. This is in fact, the product rule kind of played out. So let's undo the product rule, and what do we get? We get the derivative with respect to time of the sum over all of the I components of pi qi dot plus the partial of the Lagrangian with respect to time. Okay? So we undid, so like I said, this is the product rule. We just undid that, pulled that out here. Good, good, good. And so what is this, right? Like, what is this? Well, for many systems, the Lagrangian does not depend on time. Right? Like, the Lagrangian does not change with respect to time. So that's important. Like, we want the physics to remain the same. So, how is the system going to look between now and, 100,000 years? Are there systems that exist that won't change in that amount of time? Sure, absolutely there are, or at least generally, Of course, we have a lot of other things. There is, as we've talked about, one thing that does not follow the law of conservation of energy. Does anyone remember what that is? We've talked about it several times in the stream. And so we're going to take this quantity that's not, we're going to pull the time derivative out. And we pull the time derivative out of both of that. We're going to take the quantity inside that has nothing to do with time. And we're going to give that a name. That's the Hamiltonian. My H is crazy. I just did not expect to get that hype about H. But this shows up enough in our physics, our general understanding of physics, where we actually have a name for this. It's called the Hamiltonian. Okay? Now, you guys have seen the Hamiltonian a bunch, right? You know the Hamiltonian. So, like, what is the Hamiltonian? I'm not going to tell you yet. Okay? We want to find that out. So if we say that the Lagrangian does not depend on time,
Welcome to the channel.
that is to say,
That H looks like you are in a LA gang.
Van Buchanan. Love the name. Welcome to the channel. Van Buchanan. So if the Lagrangian does not depend on time, so if this is true, then H is conserved. Our Hamiltonian is conserved. But what is it? That's the question. We need to figure out what it is. Okay. So let's first consider the total kinetic energy of a system. Okay, we're almost done. This is going to be a really fun result. Okay, really fun result. Most of you already know the result, but we're going to do it anyways. So first,
I feel energetic about the answer.
Consider the total kinetic energy of a system, right? So the kinetic energy is equal to 1/2. This is that original one that's not in generalized coordinates. Oh, dear. And we can rewrite it in terms of generalized coordinates if we wanted to consider what our alpha is. Our alpha, Q1, Qn. I want to use little n? Yeah. So we could write it in generalized coordinates, definitely, right? H dot equals 0. We will get there soon. We will get there very soon. So I didn't actually tell you, the one system that does not conserve energy is dark energy, actually. It's free lunch at its finest. Okay, so. Differentiate with respect to t by using the chain rule. Again, this is the same chain rule. So if you do want to see this, go ahead and throw it in the exclamation mark ask, and we'll do it at the end. But our alpha dot is equal to, so now we're taking the derivative of r, and then that's going to require a chain rule for each of our individual generalized coordinates. And we're going to go sum over all of them. And it's going to be the derivative of r alpha with respect to qi times qi dot. Okay? Again, a dot is the derivative with respect to time. So you expect to find it somewhere here. It exists there. Spoiler alert, if you guys are kind of curious, it just sort of follows from, if you guys want the short and short of it, if this is just q dr over dt, then this dr dt, and then you have a physicist 1. Mathematicians hate them. But yeah, you get the physicist's 1 right here. And then you can just rewrite it like this. Okay? That's the short and short of it. Again, it's a little different if you want to, how particular you want the derivative with respect to time to be. Well, let's see here. Where are we at? So you find the scalar product, the dot product, if you will. I know that once you get into general relativity, the dot product doesn't exist anymore. The scalar
boring
product.
Math professor is gone, so no worries.
Is that boring math? Okay. It'd be really funny if that was boring math professor. So the sum over our alpha. Did he hear our mass discussion and watch the video? I hope he did. So we can rewrite all of these out. And the only reason we're really going to do this, we know that the vectors exist on the r's. Like, these are all vectors, right? I get lazy with my vectors just because we're writing them so often.
No, he is teaching.
Oh, okay. Bummer. Someone will have to go spread the good news. We've solved mass. The sum over all k, taking the derivative of r alpha, derivative of qk, qk dot. Now inside here we know that once we take the dot product of these two.
I'm right here, fools.
Anyways, the vector exists right here, so taking the dot product of the two of those gets you the scalar. But these q's, they are in fact scalars. It's the derivative of q with respect to time, but it doesn't have anything to do with a direction. So we're going to end up pulling them out in the following way. We'll redefine the kinetic energy.
Product.
I could, yeah. Yes, I could. Darn tootin'. So we're rewriting this, and we're just going to have some AJ that's going to be all-inclusive. I will write it down in a second. This AJ is it's going to be all-inclusive. It's just going to be shorthand notation. Shorthand notation for whatever the dot, or the inner product is going to be. Okay, so we have AJK, and you could write it in the terms of all of its generalized coordinates if you wanted. Why? Because they exist, right? They're just the sum. The inner product is the sum of all of the components. I did a nice introduction to dot product on, what day was it? Sunday? That's on YouTube. Oy. Can't bend over in my old age. So inside of this A exists this inner product between the two
Inner
vectors.
product.
Okay. Inner product. Bring it back. Yeah, so inside exists this inner product between the two vectors, right? Oh, they are in fact vectors. So we just have this AJK, this sort of shorthand notation for whatever this turns out to be, right? And since these are just, position vectors, it's whatever, okay? We might as well set them equal to 1. Who cares, right, guys? Right, particle physics? Okay. So, what does this turn into? Well, we're almost to the big unveil of what this Hamiltonian is, okay? We've been following the math. And the Hamiltonian is going to lead us to something really cool. So let's find out what that is. If we don't skip that. Now we have to consider again the generalized momentum. So we're going backwards this time. We're going to start with the generalized momentum. My Hagoromo chalk is misbehaving. It's not like you, Hagoromo. The generalized momentum is equal to the derivative of the Lagrangian with respect to q dot, or the generalized coordinate derivative. And inside of that, we can take the derivative with respect to with q dot with respect to the potential energy, or the kinetic energy, assuming the potential energy does not have a velocity form in it, a q dot in it. And in most systems, like I said, they don't, so we're not really worried about that. But we are going to introduce what happens if that does happen soon. Whew. So, and then we can basically say, well, if you take the derivative of this t, what do you get? Well, you get some form of this nice brief and concise notation. And what does it look like? It just
What is
sum.
energy?
Son of a gun. A I J Q I dot Q J dot. This is equal to the change in T over the change in Q dot Q I dot. There we go. Nobody said anything to me about this. That's not like you guys. Well, actually, I should say it's not like Tyrion. This is AIJ QJ. There we go. So then where does this show up? Well, looking at the Hamiltonian.
Dear Anubis, I was about to complain.
Okay, good. Okay, we're gonna fix it now. I, and then we have the generalized momentum times the QI, because we want to get to the part in the Hamiltonian where we express this. This is what we end up having as IJQ I.
I was half asleep, sorry, my bad.
You're good. I don't blame you. Q I dot. So now we just insert our generalized momentum in here, and then we bring this all through. This gets us that term that we wanted, the sum over all of Aij, all of those inner products, times Qi dot Qj dot, which we can just see right here. It's just a double sum, right? And then this is what we're interested in as 2 times the kinetic energy, not the momentum. That would be weird. If the generalized momentum gave us 2 times the kinetic energy, that'd be strange. That was my fault. I thought you were Tyrion. Man, the transformations from Tyrion into everyone else is harder and harder by the day. It's harder to tell what, the troll, it's the troll invariant. Okay, so then, now we can plug this into our Hamiltonian. That's good. This is going to equal the sum over all of the I components for our Pi Qi dot minus the Lagrangian is equal to 2t, because we get 2t from this summation right here, minus our Lagrangian, which is t minus u. Let's rewrite that. And what do we get? T plus u. So the Hamiltonian,
A
we're
good
like
troll raises
Scooby-Doo.
the tide, so everyone trolls.
So we're like Scooby-Doo. And we're like, all right, gang, let's figure out who's underneath this mask. And we pull off Hamiltonian's mask. And what is it? It's total energy. So what does that mean? Well,
2t fruity.
if Tutti Frutti. Come on. If the Lagrangian does not depend on time, i.e. the change in the derivative of the Lagrangian with respect to time is equal to 0, then the energy, the total H, whoa, easy on the H, and subsequently the total energy are conserved. But what did we start with? I mean, that was it seemed like a kind of like a long process, right, to get, we're still not done. We still have to do the magnetic stuff. Okay, this is a really fun, and the magnetic has a really cool thing too at the end, but again, you gotta stick around. This is just the first half. This is like the Act 1, okay, and we're getting to the end of Act 1, and we unveil our Hamiltonian as the total energy, and it turns out that as long as this is true, the total energy is conserved. But what did we start with? We started with time, right? We started with a time translation. So what happened? Hi, Alan. Good to see you. BMP. Everyone's a big fan of BMP. He's a celebrity. So what happens, what we figured out, okay, is firstly we just said, hey, take space invariance. Take space translation invariance. We move to a step like this. Does anything in the physics change? No, we're going to establish that. We're going to say that nothing in the physics changes. And then we followed all the things and found out that momentum is conserved. That the momentum of all of the particles in the system is the total momentum of the particles is conserved. The individual momentum is a little more dicey, but the total momentum is conserved. Now, I'm going to say this. Translate through
Welcome
in
to the
time.
channel. Things get a little bit weird.
J. Cool. Welcome to the channel. I like your name. J. Cool. Welcome, welcome. So what happens if we translate in time? What is translation in time? That's seconds ticking by, right? You go forward in time. Or if you want translational symmetry, you go backwards in time. Time. It all comes back to time, right? If you move forward in time, so now we're going to say, okay, now we're going to establish our Lagrangian by saying that if we translate through time, the physics doesn't change. What happens? Energy has to be conserved, okay? And again, there is one system where energy is not conserved, dark energy. So we're constantly translating in time in physics. True. Constantly translating in time. Something we can't stop. We are translating in time. And as you notice, if I just stand here, I'm translating. So here's my translation in space, but here is my translation in time. Nothing changed. I'm still me. Maybe round vector. You throw any more shade. Oh, man. That's funny, though. So underneath the mask of the Hamiltonian, we have total energy conserved. Did I have anything else about that? Nope, that was pretty much it. Translation through space means conservation of momentum, all done with Lagrange mechanics. Translation through time, conservation of energy, all done through, again, Lagrange mechanics.